Hello, this is Flynn Christensen and Ethan Albrecht's Mech 103 Level 3 final presentation. I'll go over a brief overview of what we're going to go over in this presentation. First, we're going to do the introduction, and we're going to talk about the specific aspirations that motivated us to do this project. And then we will go over the variables, the dependent, independent, and constant variables in our experiment. Next, we will go over the specific way that we conducted this experiment and the MATLAB and the calculations we did to calculate power. Then we will go over the specific results, and then we will discuss how the results were unexpected from what we hypothesized and what the explanation behind this was, and then also briefly talk about if we had more time to go further into depth in this topic, what we would research, and then we will conclude.
Now, as engineers, we kind of hope to make the world around us better. And a good way to do that is using renewable energy, as this cuts back on the carbon footprint overall of humanity. Now, one way to do this is through wind turbines, which is what we did our project on, where you use wind energy to generate energy. Now, we did this through constructing one out of PVC pipe and as well as wheel bearings and then some cardboard to make fins so we could test different angles.
So the variables for this project were the constant variables are going to be the fan speed will remain constant, the distance from the fan will be constant, the weight lifted, distance lifted, and size and shape of every cardboard panel will be the same. The independent variable, which will be changing, will be the angle of the blade. So there will be a 20-degree blade, a 45-degree angled blade, and a 70-degree angled blade. And then the dependent variable, which will be changing depending on the angle of the blade, will be the time that it takes to lift up 100 grams of water, 42 centimeters.
Now, our method was, as we constructed it, is that we would have a long wooden stick, which was attached to the wind turbine. So when it turned, because of the wind, it would have a string at the other end. So that would slowly wrap up and it would give us time for about 100 grams of water, which we had measured. So it would give us the general time that it took the windmill to raise that up to 42 centimeters.
So the calculations that we used to do this involved the SI units for power. We started with force, which is going to be mass times acceleration due to gravity. And then from there, we go on to work, which is going to be force times a distance. In this case, this distance is 42 centimeters. And then power is going to be work divided by time. So we can calculate the theoretical power that this windmill could generate using the amount of time it takes to lift up the weight. And this will be in watts. So I created a user-defined function to help us find the power, taking in the inputs distance, mass, and time. And then it does this by going to the similar calculations to as I previously described, and then gives an output in watts. And then after we got this output, so I made a matrix of every time from our trials. We did 3 trials and 3 different times each time. So a 3x3 matrix, and then took the matrix for the 20 degrees, the 45 degrees, and for the 70 degrees, and took the mean and then made this into a new string and then put it on a bar graph.
Now, as shown by the results put on the screen, we assumed that 45 would have been the best, being that it was in the middle of the 2 values. So we assumed that that would be the better one, as it gets the best of both worlds. But overall, it showed that 70, which was more perpendicular to the wind, so it was able to catch more of it, actually did a lot better than the other 2, unlike we had thought. And our idea behind this was that initially we thought it was because it was in the middle, but then we thought, well, to be fair, the 70 is getting more of the wind, so it pushes it more down, so it's more force going into each turn that when it hits the blade of the windmill. And overall, that kind of showed us through the results that we had found.
So if we had more time to work on this project, one thing that we are very interested in that we would want to do more research on is what is truly the optimal angle for this. And this has a lot of applications other than just windmills. It could also be involved in the angle that you put a sail on a sailboat. So how we would organize this if we had more time is we'd do many more angles and then plot many more points and then see what our distribution was looking like and which function would be ideal for plotting this.
Now, overall, what this project had taught us is a lot about how one turbines work and how, and just more concepts from this, such as like matrices for further calculus classes, as well as just how wind works in general, given how fans look and overall their degrees and how it catches them and how that can add on the ever ramping power that they use to turn the turbine itself.
And one more thing I'd like to mention about this is that this kind of topic came up in my Calc 3 class where we're calculating the normal vector to a surface or the flux integral over a surface. And when it's the surface is fully orthogonal to the vector field, you can see that the most will go, or there'll be 0. And then when it's completely perpendicular to, I don't know what I'm saying. Okay. So let me look at some of the sources that we use. So one really good source that we used for this was Engineers You Can Disrupt Climate Change. And this specific source talks about how, as engineers, we can use our knowledge to work to have a carbon net or a carbon neutral future. So that is our presentation.
Yeah.
Thank you and goodbye.
We